All right. Good morning, good evening, good afternoon, everybody. So my name is Ming Vu. I am a classmate of yours, but I'm also a biotechnology master student. And today I was tasked with providing us a short summary of this paper, the identity inference of genomic data using long-range familial searches. Um, Obviously, I'm not qualified to teach anybody anything, but I find this paper extremely interesting and I would like to take a shot at it. And this paper was written by Ehrlich and colleges in 2018 on science. So it's science, so we know that this is a very, very good study. Right, so the roadmap is quite simple today. I would like to introduce to some terms and concepts that we need to understand before we read the paper. And then we would like to introduce the paper objectives so that it's clear for everybody. We would go to methodology and results side by side and just some quick notes on the discussion that the author has provided. So, introduction to terms and concepts. I don't know about you guys, but for me, it was a little bit confusing at first. So I will start with the basic. What are we dealing with today? Well, we're dealing with genealogy. The word comes from Greek, it's, from the word genealogia, which is making a pedigree. This is a study that focuses on family, family history, and lineage. It is not an area of study. From the dawn of time, we always try to keep track of who is the son of who or the daughter of whom. If you read the Bible, you see that they always refer to someone as the son of someone else, or like Jesus, the son of God, basically. And it traditionally requires actual knowledge of the family history. So you would have to know the family to know that they have a son or a daughter. Um, not anymore, not with modern technology. So how does it work? So the paper that we're dealing with is focused on the commercial usage of this technology. And for some reason, around 2015 to 2019, there was a huge trend on trying to find if you were trying to find your ancestor, basically. So, like, if you were 12% Irish, 13% Italian, for me, probably 150% Vietnamese. I don't need to do any search to know that. But anyway, that was the big trend, and that drive up the growth of databases and technology by quite a bit. So how does it work? How do a person get their familial history done? uh, Simplified. So we would have a few parties over here. We got the genotyping service provider, also known as DTC or directly to customer provider. I put 23andMe because they are the biggest player in the market. We would have the customer, in this case us. We would have the database and our analyzer, in this case GED Match because again they are the biggest player in the field. We will also have authority, which is the police in this case. So for the customer, we would buy the kit directly from 23andMe. Usually it is a sample collection kit, saliva collection. We will spit in it and we send back the sample. They do the genotype and they send out the data. Obviously, we are, and in general, I know some of you guys are geniuses, but in general, we are not equipped very well to read this data. So what we do is that we submit it to a database or analyzer, also known as a third-party service, and we upload data over there. They analyze it, they compare it with the database, and then they would spill back the information on our family history. If you were a authority figure, say the police, and this get very simple. You just get the DNA sample from the crime scene. You send that to the database or the analyzer, and then they send back the list of possible relatives to the suspect. Now, how does the genotyping work on the 33andMe site? Uh, First and foremost, this is not sequencing. They do not sequence our data. because 99.9% of human DNA is identical with one another. So we're not doing that. We are probing the site that are known to be variable between people. There's a lot of sites like that, but they pick around 700,000 sites to probe. And now let's assume that each site have two possible outcome, only two possible outcome. Then the total recombination, sorry, not recombination, the total combination that we have is 2 to the power of 700,000. This is larger than the number of atoms in the universe. So we can assure that the chance of two people having the same exact heat map from these probes are virtually zero. Each person would have a unique heat map. It operates simply based on the principle of reverse complementary binding. We're all familiar with that. Uh, so now that you have this heat map, this probing site done, you got the data. How do you perform the ancestral analysis? We just have to understand a few concepts at first. The first one is centimorgans, and the second one is IBS and IBD. What is centimorgan? Centimorgan is a unit to measure the length of a DNA segment, but not exactly. So what I mean by that is one centimorgan on chromosome 1 does not necessarily equal to one centimorgan in chromosome 15 in terms of physical length. Centimorgan is defined at the length of a segment that had 1% of chromosomal crossover event. So the longer the segment, the higher chance of that segment having a crossover event, because this is a number game. The longer the segment, the higher chance of that having a crossover event. Now, so why are we trying this kind of measurement and we're not using base pair? Isn't base pair a lot easier to understand? And it also doesn't change from chromosome to chromosome. 500 base pair on chromosome 1 would be exactly the same length with 500 base pair on chromosome number 15. Now, let's think about this as in terms of um, effective distance. Uh, from I can go from Markham to Etobicoke, that's in Toronto, in half an hour, but they're actually only 10 kilometers apart. Uh, and in that half an hour, I can also go from my place, which is in St. Catherine, to Fort Erie, and they are around 40 kilometers apart. Which measurement is more useful? Should I use the 40 kilometers versus 10 kilometers? Or if I'm, having a date, should I just say that, oh, I'm about 30 minutes away? So they both have their own usage. So base pair is more useful when you do absolute size. So if you run the gels, you need to know the base pair number, like how long it is. But in studies that evolve around evolution, genealogy, recombination, centimorgan is actually a lot more useful, and it's traditional that we use it in these kind of study. And then we got IBS and IBD. IBS is identical by state, which just means identical sequences. It could be from conversion, evolution, horizontal gene transfer, mutation, so on and so forth, anything. As long as they are identical, they are IBS. IBD is more exclusive. It only includes cases where they are identical by descendant. For human, the IBS are usually IBD as well, because we obviously don't engage in a lot of horizontal gene transfer like viruses. Um, but we use IBD to be uh, technically correct. Usually, longer IBD mean closer relatives. it's not a set rule. So basically, if you are very if you and your brother would share more would share longer IBD than you and your first cousin, and that is the general rule. But obviously there are exceptions. But general rule of thumb. So here is the map of how people are related and how long their IDB are shared. For example, this is you, this is yourself, and this is your sibling, so your sister per se. Uh, on average, you would have around 2,613 centimorgans of IBD with your sibling. You go further away, say that you are going to your first cousin, then the length of your IBD would go down to 866 centimorgan on average. The further you go, the shorter the segment gets and the smaller the centimorgan number gets. Um, this map was uh, comprised in March 2020. You can see over here, and this was done with 60,000 known relationships. So these people are known how they're related, and then they got analyzed by the way that we did before, and these are the value. This is very useful because now if I have somebody that share between 200 to from 100 to 200 centimorgans with me, then I would know that they are probably my second or third cousin. And if that person share around 2,000 centimorgan with me, but less than 2,500, then they're probably my half sibling. You see, very very useful. So with all that knowledge in mind, let's go to the paper's objectives. The overall main objective of this paper was to introduce and showcase the strength of identity inference of genomic data using long-range familial searches. I know that's a lot of word. So basically, we are trying to identify somebody just from their genomic data. And we're doing this by first trying to find their relatives, their long range relatives, so not counting immediate family, such as siblings or parents. So to do this, the author has set up three secondary objectives. First, they set out to test the inclusivity of the method, how inclusive it is. Second, they want to test the power of elimination of this method. And then they would like to see if they can apply it in a real life scenario. So, methodology and results. First, test of inclusivity. The premise is that we have a DNA of an unknown suspect. The question is, how likely is it that she or him have a relatives in our current database? So we would assemble the data set of 1.28 million individuals who use a DTC provider, and we retain only individuals with at least two IDB segment of 6 centimorgan or more, because less than this, then they are like eight cousin or something. You can check back with the map, can't remember. But basically, they would be so distantly related that it's not very useful. And then we eliminate pair with IDB segment of more than 700 centimorgan or more, which would mean direct family or like parents or sons or daughter, because we are using long range. So this is not in the scope of this study. And then we count the individual that share the total IDB of 30 to 600 centimorgan, which would be between fourth cousin to second cousin. And here is the result. Uh, Nearly 600, sorry, 60% of such will result in relatives of 100 centimorgan or more, would be third cousin. If you are familiar with the Golden State Killer, then they found him through a third cousin. So even though to a third cousin seem, very unimportant, and maybe we never met any of them. Like me, I never met any of my third cousin. Still, it could be very useful in some cases. 15% of them would have IDB of total length of 300 centimorgan or more, which would mean second cousin or closer. And this result would only get better when the database grows with respect to population. They run a computer model and they found that this is a simulation, is not real. Um, to reach 99% third cousin found, they only need the database to reach 2% of the population. For the US, if we're looking at European descendant, that would be a database of only 2 millions. Um, this is doable. This is not a far-fetched or like, sci-fi or something. Um, and obviously, this model assume a random distribution of the population as well as random sampling, but this is a very scary result nonetheless. So now that we found the relative of the suspect, how big is the help is that? Because if we found say like 500 relatives, it's not going to be very useful either. So we would have to apply some filter to try to reduce the number of relatives that we're interested in. The first filter would be the genealogical match that we try to that we've been talking about. Then we take into the fact that for serial criminals, the place of crime is almost always within 40 kilometers of the crime scene, and we would use it to apply a filter to only include people with 160 kilometers. Very generous barrier. And then we set the age interval to be around 10 years bracket difference with the match, so plus or minus 5 years. And we assume that sex is not from the DNA. Now, from our class, we have seen cases where sex is not known from the DNA, at least not in appearance. However, those are absolutely not the majority, so we would not discuss those. So, when we apply genealogical match, we can see that from the population of 300 million people, it would jump all the way down to 855 people with total IDB around 100 to 200 centimorgans, which would be these people. So like first cousin twice removed, or like second cousin twice removed, or first cousin twice removed, and so forth and so forth, or even third cousin. Uh, so with different filters, we can see that if we limit the search to 160 kilometers from the crime scene, there will be around 369 people. We know the sex, that's 50% of them, so 185 people. With the 10 years a bracket, there would be 16 to 17 people, which is very manageable. If we watch CSI, we know that they can go through 20 suspects within 2 weeks, so it's not a problem to the police at all. And if they also consider if the person was a subject of any previous research, because if they were and then their genome was sequenced, then the law permit the, the investigator to get the birth year of that person. Now with the birth year, the age resolution go down all the way to 1 year instead of 10-year bracket. And with that information, there would only be 1 to 2 people left, which is a piece of cake. So to sum up all the filter, we go from the entire population of USA to 16 to 17 suspects. So the power of elimination here is immense. Now, does it hold up? All of the tests that we did was only hypothetical. How does it do in a real flight scenario? So the premise is that we have the DNA sequence of an actual human. The question is how hard it is to re-identify this person. Now the method is simple. They would obtain a genome of a woman from the 1000 Genome Project, which is publicly available, with some prior knowledge. We know that she lived in Utah. We know that she had European ancestry, which actually is deducible from the genome itself, so it's not new. But the new thing is that she lived in Utah and that she was alive at the time the sample was taken. At least we know that. We don't know if she's still alive or not, and we don't know her age either. Um, uh, but when we search for a match through GED match, we would then apply the filter, so we would have approximate age, location, ancestries, and we know that she's a female. So here's the result. The search on GED match found two males that share 180 and 171 centimorgan with her, respectively. These two males share between them 62 centimorgans, which indicate a ancestor of 4 to 6 generations back. Now, this common ancestor of the two males was identified to be an ancestral couple within 1 hour. So astonishing speed. It's only 1 hour and they already found a common ancestor. From the ancestral couple, they would scan the descendant to find the person with the fitting markers or with a fitting filter. So like age, location, sex, ancestry, and they would find the targeted woman again. Um, in the paper, they say that this took much longer as the ancestral had 10 kids and then hundreds of descendants. Um, but they did it in a day. So uh, taking into account the sample acquisition, then data analysis, then results, they probably can do this within 2 days, um, which is insane from my perspective, because I've been involved in with a lot of phylogenetical analysis, and um, 2 days of work is basically nothing. You could do it very easily. So now that we have done all of the result, let's look at the discussion written by the author. The main point that the author trying to raise is their concern. They're very concerned that the same technique could also be exploited for harmful purposes, such as re-identification of research subjects from the genetic data. Um, we are all familiar with the Witness program in the U.S., where they try to protect people that come out against crime. With this kind of technology, that the identity can no longer be hidden because you can change your name, you can change your birthday, you can change your address, phone number, but you cannot change your DNA content. You can go through surgery, like plastic surgery, to look completely different, or even switch your gender, but your genetic data is stuck the same throughout your life. Uh, More importantly, they can also file your relatives, and that could even be more significant than filing yourself. So very, very concerning. That's such a powerful technique could fall in the wrong hand. So they advocate for a high level of data security by treating genomic data as identifiable data. Uh, Now, if you have done some, like human research, you know that identifiable data is treated very, very stringently, very strictly. Uh, to have access to the kind of data, the research group would, or anybody would need a much high clearance to access them, and it would require very stringent procedure to collect, store, distribute, and use. For example, um, if you take part into a research to a scientific research, and they want to collect your name and date of birth, those are identifiable data. They would have to inform you the significance of this collection, explain to you their usage, and then have you sign a consent form after you are fully informed and fully understood the significance of this data. So if DNA data was also treated as identifiable data, this kind of procedure has to be gone through. Other identifiable data are name, birthday, SIN number, address, phone number, etc. And they also they advocate for they also advocate for that kind of clearance, but they also advocate the usage of cryptographically signature. So in their proposal, the DTC provider should cryptographically sign the text file containing the raw data available to customers. Now, I'm not familiar with cryptographic signature. I'm not a bioinformatician or biologist to be exact. But anyway, what it means is that the DTC now have to put in a signature in their file so that the third party service, when they receive that file and receive that request to use the database, they can know that, oh, this is from a trusted DTC provider. Imagine that if you are a crime organization, right? You have your own lab and you have your own suspect, and you sequence them, not sequence, but like genotype them, and then you would send this genotype to the third-party server to use the database. Now, the third-party server can deny your access because even though you got the genotype, you don't have the signature from a trusted DTC provider. And you can very well have the data, but if you don't have the database to compare it with, then your data become a lot less valuable. So those are the suggestion and discussion from the author, and that would also end today's presentation. Thank you very, very much for listening. I know that I am not a very good explainer, as for me it is also still kind of confusing at times. So I look forward to discuss with you guys in the lab, in the class, and if you have any kind of question or note that you can help me improve on, please do. All right, thank you very much, and have a good rest of your day.